Good afternoon all. Welcome to the post-lunch session. I am Vishnu from Raman Research Institute. The first speaker of this session is Victor Mukherjee, and he will talk about many-body finite-time quantum engines.
So thank you, and thanks to the organizers for organizing this and for the invitation and giving me the opportunity to present our work here. So I'll be talking about many-body finite-time quantum engines. So these are mainly based on these three works. I think Revati was probably in the audience. Okay. So first is before I go into engines, like what I mean by engines, or more specifically, in this talk I will talk about these quantum critical engines. What I mean is, like in a classical system, we know an engine is a container of a gas and there is a piston and heat flows from some hot bath to the gas and some of it goes to a cold bath and the rest we get out as work. Similarly, here the idea is the same, very similar. The difference is instead of the container of gas, we have some quantum system. Here specifically, I consider a many-body system close to criticality. So it is taking heat from a hot bath, converts part of it to work, and the rest of the heat flows to a cold bath. So what the main message of my talk will be that quantum critical engines show universal features in their output. And this is in spite of the dissipation that is always present in engines. And also we have the notion that quantum technologies need very low temperatures close to absolute zero. But what it appears is the absolute zero may not be always needed or even optimal for operation of quantum engines. Okay. And these are not always like theoretical considerations. Also, in the last few years, there are several experiments. For example, using ion traps, NV centers, NMR qubits, superconducting qubits. For example, here they used ion traps to trap a calcium ion and could make a single atom in heat engine. It was still not quantum because the temperature was quite high, but they made an engine with a single atom. And also with, I think this is with NV centers, in which they could show that with a coherence in the initial state, they could get a higher work output compared to without coherence. That showed that there is a quantum advantage present. And there are also several other experiments. Okay. So these are very much like experimentally realizable, what I will talk about. So the overview is, first I will start with universality in many-body quantum critical engines. So that will depend on these quantum phase transitions and Kibble-Zurek mechanism. And I will focus on a free fermionic working medium. And then I'll show that this universality also says that this finite time actually reduces the performance of quantum engines. So how can we use control to improve their performance? And finally, quantum critical engines at finite temperatures, which is, I think, a more practical case. And finally, I will conclude. So, just to remind you, this this universality will depend on this Kibble-Zurek mechanism, which basically says that there is a adiabatic impulse approximation when we drive a system through a quantum critical point. So the energy gap that goes to zero at the critical point, lambda is equal to lambda c. And there is an inherent time scale in the system given by this time energy uncertainty relation 1 by delta, where delta is the energy gap. And there is also another time scale given by this rate of change of the Hamiltonian, delta by delta dot. So there is always a competition between these two time scales, and whichever time scale, whichever wins, sets the behavior of the system. So close to criticality, when the inherent time scale is very large, does not matter how slow we drive the system, it is always going to get excited, and we always get into the impulse regime with excitations here. But away from criticality, delta is large, so the energy gap, so the time scale is small. So we can have a adiabatic dynamics, and this adiabatic impulse approximation can also be used. I mean, one can use the one can find the Kibble-Zurek scaling form which depends on this kind of approximation, which is related to this approximation. So basically, say if we drive the system, this parameter lambda linearly in time with a rate tau, then this defect density shows a universal scaling with respect to this rate of quench tau, that is tau to the power of minus nu d by nu z plus 1, where nu z d all are critical exponents. I mean, till now it has nothing to do with engines, it is just quantum critical systems driven out of equilibrium. And this also shows that the excitation energy that also is related to this defect density, and it also shows these universal scalings for quenches across the critical point. Here quenches means slow quenches as a function of some with some finite rate. Across the critical point, it gives this scaling tau to the power of minus nu d by nu z plus 1. But if we quench till the critical point, there is some change, that is, it becomes nu d plus z by nu z plus 1, where d is the dimension, nu is the correlation length exponent given by this relation, xi is the correlation length, this is the distance from the critical point, and z is the correlation time exponent. Okay. So now I will use this in this kind of an engine, which is an Otto cycle, which is a 4-stroke cycle. So here, say we have a many body system, which can be any many body system or even a single body system, does not matter. But in this case, as I said, I will talk about many body. So say we start with this at this point d at some parameter lambda 2 of the Hamiltonian, and we do a unitary stroke from lambda to lambda 1, say across a critical point shown by this red line. At A, we couple it to a hot bath, which can be a non-thermal bath also in principle, but it should give energy to the system, energy Qn. And the lambda is constant at lambda 1, then it reaches B, which is a high entropy state. At B, again we decouple it from the bath, we take lambda 2 from lambda 1 to lambda 2 across the critical point, and at lambda 2 again we keep the Hamiltonian constant, couple it to a cold bath, so that part of the energy is dumped, and again we reach D, so that we have a cyclic process. And this dumping of energy is essential because of the second law of thermodynamics, and this Q in minus Q out, that gives the work output. Here the sign convention is that energy is positive if it enters the system, so this modulus. But in any case, the quantification is given by the work output, that is the heat input minus the heat output, the power, that is the work divided by the total time, and the efficiency, that is how much we get out divided by how much we invest. So the idea is how to have engines with very high values of these parameters, and if quantum mechanics can somehow help us in achieving that. Okay. So the problem is, when we talk about this using Kibble-Zurek mechanism in this kind of setup, immediately we see that there are thermal fluctuations which can dominate the dynamics, dominate the quantum fluctuations at all non-zero temperatures, and that can destroy Kibble-Zurek mechanism. And also there are multiple unitary and non-unitary strokes in addition to thermal fluctuations, which can again destroy the Kibble-Zurek mechanism or destroy any universality. So whether we get universality or not is a non-trivial question in this kind of settings. So for that, what we do is, we again look at the cycle and we say that let's start with this temperature of this cold bath going to 0. Towards the end of the talk, I will remove this restriction, but for now, for getting the universality, let us look at this. Say T goes to 0, so that we are close to the ground state at D. Then we cross the critical point, and then this Kibble-Zurek mechanism gives the excitation energy following this universal scaling law. And here we couple it to a Markovian bath, so that the final steady state is independent of the initial state. We go to a final rho bar, which is independent of whatever the state is at A. And if the entropy is high enough, that is the temperature of the bath is high enough, then one can show that at C also its state is same as that at B. Or if there is a fast quench, in either case the state does not change from the B to C. And here again we couple it to the cold bath. So in this cycle, what happens is, only problem is because of these excitations, it reduces the heat input in this A to B stroke. So now what we can we see is that the output work is again this thing, heat input minus the heat output, but the heat input is given by the heat input in the adiabatic limit when this tau, that is this tau is infinite, minus the excitation energy where the excitation is due to these non-adiabatic excitations. And this excitation follows this universal scaling laws. So using this, one can show that this in the unitary stroke till the quantum critical point, this work output minus the work output in the adiabatic limit, that is when tau is infinity, this thing shows a universal scaling given by this tau to the power of minus nu d plus z by nu z plus 1. This is if we quench till the critical point, but if we cross the critical point, the scaling changes to this. So here what it shows is that just the work output will not show universal scaling, but this difference will show. And so what we have shown is that these universal scalings can be shown in these finite time quantum auto engines under very general conditions, which at the cold bath has to be at very low temperatures. The unitary stroke d2a is at a finite rate tau, which gives these scalings. This energizing bath takes it to a unique steady state, that is, it has to be a Markovian bath. And the unitary stroke from B to C is first, or the entropy has to be very high in the hot bath when it is coupled to the hot bath. And once these conditions are followed, we get universal scalings. And we also get these scalings also translate to this power output, everything. So the power output is this total work output divided by the time, which again shows the scalings universality here. Here x is equal to 1 or 2 depending on whether we quench till the critical point or across. And also one important parameter is when we get the maximum power, the tau. So for very small, for very fast quench, non-adiabatic excitations reduce power. And for very slow quench, large tau, this power again goes to 0 because tau is in the denominator. So in between at this value, we get the maximum power. And efficiency at maximum power is also another important factor, which again shows, part of it shows this universality. So the point is, when we have this criticality, different parameters show universal scalings, which basically connects these two fields, quantum phase transitions with thermodynamics of quantum systems. And one can use these universal scalings to make these optimal quantum engines. For example, one can then choose materials which has appropriate critical exponents, which will give the maximum power work output. Say, for example, if we just increase the dimension d, then this will decrease and the work output will approach the adiabatic work output, even for finite tau. And technically, the way we do this thermalization strokes is we consider a free fermionic medium so that the fermions are not talking to each other. And the fermions there, the thermalization is given by this Lindblad operator, where we consider, say, these are fermions coupled to hot and cold baths. And the baths, in this case, we have considered this non-local kind of bath, non-local in free space, but in fermionic space it becomes local, so that each fermion is coupled to its own local bath. But again, even if we consider just thermal baths, local thermal baths, the results do not change. So this CK dagger are the annihilation creation operators for the fermions. So using this, we could get the steady states and all the relations, and we could verify it, the relations. So for verification, we use this transversizing model, where there is this criticality at H is equal to 1 between paramagnetic to ferromagnetic transition, and we can go across this transition or till this transition and make this engine. And these are the, we verified numerically. So this again, this difference W minus W infinity, it shows this scaling tau to the power of minus half. If we quench across the critical point and till the critical point, it is tau to the power of minus 1. And this power and efficiency are given here. As can be seen, for very large tau, when the non-adiabatic excitations are very low, both the efficiency is large, but as we decrease tau, the excitations dominate and the efficiency decreases. And similarly for power output, there is an optimal tau at which we get the high power. Same, it does not, I mean, qualitatively it is same whether you can steal the critical point or across the critical point. Okay, so that brings me to the end of the first part of my talk. So there is universality in work, power, efficiency at maximum power in quantum auto engines operated close to quantum phase transitions. Universality may help in designing optimally performing quantum engines, for example, by choosing materials with proper critical exponents. Now, this also shows that, again, the universal, these laws also show that finite time is actually bad for quantum engines because there are excitations which reduce the output and work output. So what is important is we need to apply control to improve the performance. So it is like adiabatic or slow dynamics enhances the efficiency, but it will lead to engines with zero power because the time appears in the denominator. But non-adiabatic excitations, non-adiabatic dynamics, that is first dynamics, will result in finite output power, but again it will reduce the efficiency of quantum engines because of these excitations. So the questions one can ask is, how can one improve the performance of finite time anybody quantum heat machines through control? Now there are different kinds of control available, such as scrap, where one can do a numerical optimization, or say by bath engineering. Here the control that I will talk about is shortcuts to adiabaticity, which is an analytical form of control. So here the main idea is, first let us look at just simplest case, a Landau's in a transition of a single qubit. Say these are the sigma z, sigma x, they do not commute. So of course as we change this time t, there is excitations in the system. So say we start from the ground state here at time t is equal to minus infinity or some minus large value say. Then what we want is, say as we change time, the system should always follow the instantaneous ground state. But what happens in reality is that initially it remains in the ground state, but when the energy gap is small, there are non-adiabatic excitations when because of the time scale 1 by energy gap becomes large. So there are excitations and the system eventually ends up a part of it in the higher excited state. So, and these non-adiabatic excitations reduce power or efficiency in the quantum engines. So how do we eliminate those excitations so that it always follows this instantaneous ground state given by these red lines? That is the question. And this should also increase the performance of the engines. So another possibility is also going, another part of shortcut to adiabaticity is also we don't care what happens in between. We go across this blue line just from initial to final state. That is a kind of a quantum speed limit, but I am not going there. So I will focus on a control which allows us to follow this red line. So what this shortcuts to adiabaticity uses is, in general what we have is when you solve a Schrodinger equation, usually we are given some original Hamiltonian H0, which is the Bayer Hamiltonian. I will call it Bayer Hamiltonian. And for this Hamiltonian, what psi we get by solving this equation. That is the usual problem. But here we turn it upside down. Here we ask that we already know what psi we want. The psi is the, of course, here psi is always this ground state. So given a problem, we know that psi we want is the adiabatic psi. So we ask the question, what Hamiltonian will give us that psi? So we solve for this HSTA. That is H shortcuts to adiabaticity. So this HSTA can be given by this original Hamiltonian H0 plus some factor lambda dot A lambda, where lambda dot is the rate at which the Hamiltonian is changed. So if we change it very fast, the control term will be of larger magnitude. So one can show it quite simply. So say we have this Schrodinger equation, and then we apply, if we have an unitary, that is change of basis to the moving rotating basis. So then one can show that this psi tilde, that is this unitary rotated psi, that follows this equation with this Hamiltonian changed to H tilde, that is the unitary rotated Hamiltonian minus this lambda dot A lambda, and this by construction U is such that this H tilde is diagonal, so this H tilde cannot cause any excitations. All the non-adiabatic excitations come from this lambda dot A lambda term. So the idea is in the control we add an additional lambda dot A lambda to cancel these terms, which give rise to the off-diagonal terms which cause excitations. So if we add this lambda dot A lambda term, finally in the Hamiltonian becomes just diagonal in the rotating basis and all the excitations are eliminated. But the problem is this A lambda, it actually has this form. So what it means is even though it has a very nice compact form, but it depends on all the energy spectrum. So we need a full knowledge of the energies of all the levels. And that is usually not possible for many body systems, which can have a 2 to the power of n number of energy, n number of variables. So in any case, what we will do is we will apply a approximate form of shortcuts to adiabaticity. And the way we do it is, again, say we have an Otto cycle with 2 unitary and 2 non-unitary strokes, and we have the working medium here, the spin chain. So there we have the original Hamiltonian, plus we apply another HCD counter-diabatic Hamiltonian for the control. So we will do it in a spin chain kind of system. So we have this spin chain with transverse field, longitudinal field, and the nearest number interactions with disorder. And here, this is a many-body system, so the exact form of counter-diabatic Hamiltonian will involve a many-body interactions, which is difficult or almost impossible to implement experimentally if there are, say, 6-body, 100-body interactions. So instead, what we say is we apply a approximate protocol suggested by Sales, Polkovnikov, and also others in 2017. So there what they say is that, look, the original actual Hamiltonian may be difficult to implement, but by variational principle, one can have a good approximation. So here the approximation is what we say is, let's look at a single body term. Even though the exact will have also multiple body terms, but for a start, look at the single body term, and this Yj, this prefactor, is the thing that we want to optimize. And by optimization procedure, which if someone is interested, we can discuss later. So this optimization procedure gives us this result. So again, this is just single body terms, no interaction is involved in the counter-diabatic in the control protocol. Then what we find is immediately this power P, so this is power output as a function of this total time period tau. So without control, which only H naught, the power output is positive. Positive means that we are not getting any power output, we are investing energy. So the system is not acting as an engine. So for it to act as an engine, we need a negative power. That is, power is coming out. So when we apply our control protocol, what we see is immediately we get a large negative power, that is, we get power output, and that is just with a single body control term. And this is just this zoomed in form. And here it is the what it shows is the work output because of this H naught plus HCD. Let me just go back show you. So H naught is the original Hamiltonian, HCD is the control part. So this WCD is kind of a cost of control. The cost, that is the energy that one needs to invest to apply this control. So what it shows is, first, this part, this is a work output is positive from the additional control term. What it means is, in this regime, the system does not act as an engine, rather it acts as a hybrid engine plus battery kind of system, because we are investing also work output from the control. But other than that, for small tau, it acts as an engine with quite significant power output because of the control term. And this was done with 8 spins. with disorder, with exact diagonalization. And also one can look at the efficiency. So the rate is the efficiency without any control. As one can see that for very large tau, the system is almost adiabatic because there are no excitations, does not matter whether there are control or not. Excitations are almost zero. So the efficiency, this dashed line is the adiabatic limit. So even without control, the efficiency approaches the adiabatic limit for large tau. But as soon as tau is small, the efficiency without control reduces to zero very fast. That is, we cannot use the engine in this regime. But as soon as we apply our control scheme, we see that even though it is not perfectly adiabatic because we are using approximate control, but still it is a very high efficiency compared to without control case. And this is the fidelity. So fidelity between the for the different strokes between the time evolved state with or without control and the instantaneous ground state. So the rate is the fidelity with the for one of the unitary strokes without control. As we see again for very large tau, it is fidelity is 1, that is it is following the ground state. But for small time, fidelity is almost 0, that is it gets excited. But with control, the fidelity is almost always very close to 1 except some small time in which it does not act as an engine. So in different ways what we check that the control scheme is actually giving a very good almost adiabatic operation with very high power output, very high work output and also efficiency. Okay, so what I have discussed till now is the universality in these finite time engines, but there and also after that how one can use this shortcut adiabaticity to increase those performance. But all of this where they had this kind of a impractical this idea that one of the these cold baths has to be at a very low temperature. Close to 0 temperature, but of course that is not always possible in practice. So next what I will talk about is, say the same engine, but if the cold bath is not at close to 0 temperature, so it is a finite temperature. In that case, of course, there will be thermal excitations. So again we start with the, we have a same kind of a setup, but we have the cold bath at some finite temperature Tc. And we start with the working medium, that is the spin chain in a thermal state at temperature Tc at D, which can be at the, D can be at the critical point or on one side of the critical point. And then we drive the system to A, far away from criticality. Now, what it has been shown in this paper and some also other papers by Polkovnikov and others, that in that case, for this finite temperature, the defect density at A is given by the defect density at 0 temperature, that is when Tc is 0, multiplied by this tan H term. This epsilon is the energy of the system at the initial time and Tc comes in the denominator. So in the limit when Tc approaches 0, again N approaches N0, that is the 0 temperature limit. But when Tc is very high, this just becomes kind of 1 by Tc form. So then for large temperature, that is when this temperature of the cold bath much higher than the temperature than the energy scale of the working medium, this defect density is tau to the power of this minus nu d plus z by nu z plus 1 divided by Tc. And this again we have the same kind of a scaling form in this W minus W infinity, which is 1 R by Tc tau to the power of this critical exponents. Now what it shows is, again, good operation means, say in the adiabatic limit we have the high work output because there are no non-adiabatic excitations. So what our aim is for this W to approach this W infinity. And what we see is from this relation that W approaches W infinity for this tau much larger than some tau minimum, where tau minimum is given by this some factor, constant factor R, which depends on the system, which can vary from system to system, divided by this temperature of the cold bath to the power of these critical exponents. So what it shows is, as we keep on increasing Tc for higher the temperature, lower this tau minimum. So for high temperature of the cold bath, we may not even need shortcut to adiabaticity because the time period might already be larger than this tau minimum. Right? So we may not need shortcut to adiabaticity for finite temperatures if tau is larger than tau minimum, and that is very much possible because for high Tc, tau minimum becomes very small. Okay. So we also verified that numerically. So this is the work output as a function of this tau for different temperatures. So as I said, that this shows that we should expect the adiabatic limit for a tau which decreases with increasing Tc. So for high Tc, low Tc, Tc is equal to 0.1, what we see is that as we increase tau, the work output increases because excitation is reduced. Finally, it saturates to the adiabatic limit for large tau. Now, if we increase Tc to 1, what we see is again the qualitatively similar, but quantitatively it saturates much earlier. So what it means is as soon as this tau becomes larger than this limit, we do not need any control to improve the performance of the engine. But this does not mean that high temperature is good for quantum machines. Actually, what is happening is that thermal fluctuations dominate any quantum fluctuations. So applying control to reduce quantum fluctuations does not really improve the engine. So this also one can see from this work output as a function of this Tc. For small Tc, the work output is large, but as we keep on increasing Tc, the work output decreases. And the tau minimum also decreases linearly with Tc following the scaling relations given here. So what it shows is that both work output and this tau minimum both decrease with increasing Tc. So what it means is that the power, that is this work output divided by the tau minimum, can even increase with increasing Tc. And that would mean quite counterintuitively that higher temperatures might actually benefit the operation of the quantum engines. And that is actually what we see here. So again, this W approaches W infinity for tau larger than tau min, and tau min decreases with increasing Tc. So this ratio may increase, and that is what we see here, the power output as a function of Tc. So this is, we get an inverted parabola kind of thing. So for small time, so small temperature or large temperatures are not the optimal. We get the optimal regime somewhere in between, which shows that this optimal temperature for this operation of the engine is not the absolute zero, it is somewhere in the middle. But of course, it depends also on the constraints available on the setup. So finally, this brings me to the conclusion, that is, quantum engines with interacting many-body working mediums present a rich field. And what I have shown is that there is universality in work, power, efficiency at maximum power, close to phase transitions. And for any finite temperature, these thermal fluctuations dominate for large tau. That is, it dominates over any quantum fluctuations. So any control which only reduces quantum fluctuations are not enough for finite Tc as long as this tau is large. And that also shows that we may not need absolute zero temperature for optimal operation of quantum engines. So, thank you.
I had a naive question regarding the counter-diabatic part of your talk. So is the counter-diabatic term unique for a set of states, like in the context of, let's say, quantum annealing and start from a state and I want to go to another state? Then is it unique?
It depends on this energy spectrum. So if the energy spectrum and the eigenvectors are same, then I would expect they should be same. But usually it will change from setup to setup.
Because I see there's this U matrix there, which is like delta lambda U, which you convert to A, right? Or,
Yes.
So U spectrum.
U is the unitary that allows the it is the unitary that allows the Hamiltonian to be diagonalized in the moving frame.
Okay, fair enough. And the other question is this locality of this approximate counter-diabatic term which you found here, which is sigma. How did you get that? I missed that part. Why did you choose sigma y?
Okay, so this one, it shows that the actual counter-diabatic term will actually also involve many non-local terms.
Yes.
But we say that non-local terms in principle, experimentally, it might be very difficult to implement. So we just have a local term with some prefactor yjt, which we can optimize.
Okay.
And optimization will give us to the most closest form to the counter-diabatic, exact counter-diabatic, given the constant that we have only single body terms.
Okay. And does this work if your lattice is not say linear, like in quantum annealing you sometimes solve max set problems and stuff where can you still figure out a local kind of counter-diabatic term to make these things work?
So you mean when lambda is not just t by tau, it is like t squared or something?
No, I'm just saying the connectivity between the sites is not like in a chain. It's like, let's say, randomly connected.
Okay, I have to think about it.
Random graph.
I have to think about it. I cannot.
Okay. Thank you.
It was fine. Are there any more questions?
So it's a very simple question. So if you really want to make the engine more efficient, wouldn't you altogether avoid a critical point? Because you know, if you go to the critical point, you will anyway generate entropy.
Right. So
which is not good for an engine. Yeah.
Exactly. So criticality, we use that for looking at the universality. But I mean, these non-adiabatic excitations also appear even if there is no criticality. For example, in this model, there is no critical point. We are not going to a critical point. But still, there is a lot of excitations.
That's fine. So that was just to study the universal behavior.
Universality, and that also allows us to have this control without knowing the details about the materials.
General question. I mean, so in normal engines, I mean, when like if I take a Stirling engine, you just put it in contact with two reservoirs and it starts working, right? And you can get work out of it. In this kind of engines, like usually you have this time-dependent driving protocol which you have to put in by hand. So it's not clear how you really extract anything out of it.
Okay, so this work output, you mean that by hand you are also investing some work out? Okay. So yes, that also takes that into account. So say in one of the strokes you will get say positive power work output. In the another strokes you get negative. So the total sum total should be so that we get the ultimately to be output.
But in real engines, you don't have any such time-dependent protocol. Right?
No,
it
actually,
just runs on its own.
You mean real engine like a combustion engine kind of thing that I guess you're talking about?
It's like a simple Stirling engine if I take. It
Yeah,
just runs.
so, okay. Real means, okay, classically also this Otto cycle is originally a classical engine. So there also, I mean, classically also you can have this kind of a four-stroke thing.
On its own, I'm saying. All you need is heat baths.
No, I mean, that is actually, I think, combustion engine does that. But in any case, so even that one has this autonomous engine which runs on its own, which is probably closer to what you say. But there also the total details are more or less the same, the working principle. So finally, what I think you're saying is that if we are investing work, then how are we saying that we are getting work output? So this investing work also takes that, I mean, it takes that things into account, that how much work we are investing and how much we are getting out. So if that sum total is actually negative, then we say that we are getting something out. But I agree that in practice, when we actually implement that, autonomous engines might be more important. So in that case, say time crystals or those things, people are working on those autonomous engines.
If there are no more questions, let's thank the speaker once again.